the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are currently going through a conversation about the row space of a matrix. And we are going to go ahead and create an efficient method for computing the bases for column space of A, null space of A, and the row space of A. This is somewhat of a short video, so hold on. Here we go. We'll start with a little note here. The pivot columns of a matrix A give us a basis for the column space of A. This is done by first finding an echelon form of A so that we can find those pivot columns. Now for this conversation, we'll go ahead and call the echelon form of A, or I should say an echelon form of A ref. And there's a little footnote there, and that footnote down below is just saying that this is a very common notation, meaning the row echelon form of your given matrix A. So finding the basis for the column space of A really requires the row echelon form of A, and then you have to jump back to the original matrix A to state what the basis vectors are. They're associated with the pivot columns you found in A ref. Now, finding the null space of A further requires us to find the reduced row echelon form of A. Let's go ahead and call this reduced row echelon form of A sub RREF. A sub reduced row echelon form. Once we find the reduced row echelon form of A, we solve A sub RF X is equal to 0 to get the basis for the null space of A. So again, somebody comes in the room, they hand you a matrix, you have to get to a row echelon form for that matrix, and then to the unique reduced row echelon form of that matrix. Finally, since the reduced row echelon form of your matrix is, well, an echelon form of your matrix, the non-zero rows of the reduced row echelon form of your matrix gives you a basis for the row space of A, and that's from a theorem that we just covered in the last video. This theorem right here. If A and B are row equivalent, their row spaces are the same. Also, if B is an echelon form of A, and by the way, B could be a reduced row echelon form of A, that's also an echelon form of A, then the non-zero rows of that reduced row echelon form of A form a basis for the row space of A. Therefore, the ultimate goal in finding the bases for the column space of A, the null space of A, and the row space of A is really to find the reduced row echelon form of A. And remember, the reduced row echelon form of A is unique. That's why I'm saying the reduced row echelon form of A and not a reduced row echelon form of A. What's kind of staggeringly interesting about this is you spend all of linear algebra learning really high-level theory when you likely walked into the course being able to find the reduced row echelon form of a given matrix. And here we are, around halfway through, maybe a little bit further than that, and you find out that the end-all be-all to finding the bases for the column space, row space, and null space of a matrix A is to get that matrix in reduced row echelon form. Let's put this to practice here. Find the bases for the row space, the column space, and the null space of this given matrix. And I kind of did this in a previous example, but I'll go ahead and do it again here. All right, so we have put this matrix into reduced row echelon form through a lot of little arithmetic. Hopefully, no arithmetic mistakes. The easiest things to read off right now are the basis vectors for the row space of A, which are going to be the non-zero rows of the reduced row echelon form of A. And I'll write that up here. I apologize if the screen jumps back and forth while I do that. I have to keep zooming out and zooming in to read the vectors, but that there is the basis for the row space of A. The second easiest basis to write down is the basis for the column space of A. Note that I squared up the pivots there. So the first column is a pivot column, the second column is a pivot column, and the fourth column is a pivot column. Now remember, with the column space of A, it requires you to go back to the original matrix and grab those related columns. So we'll go back to A here, grab the first, the second, and the fourth columns of A, and those will be the basis vectors for the column space of A. All right, we have those two written down, the basis for the row space of A and the basis for the column space of A. Finally, the hardest of the group, and it's not hard, it's just the extra mechanical bits necessary to find the basis for the null space of A. Well, that requires us to go back down to our reduced row echelon form here. We can easily see our free variables are x sub 3 and x sub 5, so I have to write the other variables in terms of those two free variables. Now, of all the bases, the null space is the one that's not super obvious. We get that x sub 1 can be written as negative x sub 3 plus 3x sub 5. By the way, you'll have to forgive me. I'm imagining that there's a a column of zeros right there, and I'm just solving over. I just don't like to write that in there. X sub 2 is negative 2x sub 3 minus 5x sub 5. And then x sub 4 is just the opposite of x sub 5. And again, x sub 3 and x sub 5 are free variables. So a solution, or any solution to the homogeneous equation, can be written as follows. Hence, these two vectors right here form the basis for the null space of this matrix. All right, so we have found successfully the bases for the row space of A, column space of A, and null space of A. Very nice. It's such a wonderful example because it really does lead you through everything you need to know. Now, I'm not going to talk about the dimensions of these yet because I'm reserving that for the next lecture. However, a little bit of a warning. Since row operations do not preserve the linear dependence relations among the rows of a matrix, you must use the pivots of A ref or A R ref as the basis vectors for the row space of A. Now, this is a very wordy way of saying the following. If you take a look at the reduced row echelon form of A, you might say, oh, the first three rows of that reduced row echelon form of A are therefore linearly independent. Therefore, the first three rows of A itself must be linearly independent. But that's not necessarily true. A very simple example to showcase that that is not necessarily true is when you're performing the row operations to get this matrix into reduced row echelon form, you might have swapped, for example, rows 2 and 4. Once you do that, while your final matrix will always have, in this case, the first three rows being linearly independent, that was only because you had to row swap at some point, or you chose to row swap at some point. So the original matrix, rows 1, 3, and 4 could have been the linearly independent rows with the associated pivots. So I'm just letting you know that the only time you actually go back to the original matrix to grab vectors to throw into a basis is when you're dealing with the column space. Row space, you'll always talk about the rows of the reduced row echelon form of your matrix generating the row space of A. And I should say the non-zero rows of the reduced row echelon form of your matrix generating the row space of A. Anyhow, I hope that was okay. I know that last little part's somewhat confusing, but for the most part, very mechanical video. I hope this is somewhat helpful for you, and I hope you have a wonderful day. Be a great human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.